Here are solutions to homework set number 2 for ECE 463-663 Modern Controls. This homework set looks at state space, eigenvalues, and eigenvectors. The first problem is, given this RLC circuit, find the transfer function from V0 to V2. To do that, we're going to use state space and state variables. For an RLC circuit, the energy stored in the current in the inductors, voltage on the capacitors, and the basic equations are that V is L di dt, and I is C dV dt, or Asmy's derivative. So every time I have an inductor, I add a first order differential equation. Every time I have a capacitor, I've got a first order differential equation. To come up with the dynamics, if I can specify the voltage and the current, I've got the dynamics. For example, for the first capacitor, the current I1 is C dV dt, 0.01 times the derivative of V1. And in my book, S and derivative are interchangeable. That's kind of what the plus operator means. That's equal to I4 minus I5 minus I3. And I3 is V1 minus V3 over 50. The second capacitor, I2 is C dV dt, 0.025 Sp2. I2 is equal to I5 minus this current. That's just V2 over 100. I3 is C dV dt, 0.02 Sp3. That's V1 minus V3 over 50. So that handles the capacitors. To get the voltage, this guy right here, that's your 0.2 Si4. That's equal to the voltage across that inductor. Voltage on the left is V0 minus 3I4. Voltage on the right is V1. For this inductor, V5 is L di dt. That's 0.25 times Si5. That voltage is the voltage on the left. That's V1 minus 4I5 minus the voltage on the right, V2. So these are your 5 equations that describe the system. On a test, you would leave it right there. On homework, I can convert to state space, throw that in MATLAB, and find the transfer function. So this is where MATLAB really shines. Solving those equations by hand would take about 2 hours. In MATLAB, about 5 minutes. To solve in MATLAB, I solve for the highest derivative and group the terms. It gives me these 5 equations. Now put that in matrix form. So to make the states, V1, V2, V3, I4, I5, and order doesn't matter, just have to be consistent. If I choose this order, then the first equation is, I'm kind of reminder myself, this is times V1, V2, V3, I4, I5. SV1 is 100 I4, this term, minus 100 I5, minus 2V1, plus 2V3. So there's the first equation. The second equation, SV2 is 40 I5, minus 0.4 V2, likewise for all the rest. Gives your A matrix, B matrix. What I'm measuring is V2. That pulls off the second state. Here's your C matrix, and the D matrix is 0. Now that I have A, B, C, and D, I can throw that in MATLAB, input A. I ran out of space, so I just put in the first 3 lines, added to it the next 2 lines. Here's your A matrix, B matrix, C, D. Throw that in MATLAB in state space, find the transfer function. There she is. Problem 2. Find a first or second order approximation for the system. So here's the system. Here's your dominant pole. Definitely keep that. Keep all the poles and zeros that are within 3 to 10 times that pole. Ignore everything that's more than 3 to 10 times faster. So I'll keep this pole. This 0 is about the same amplitude. Keep the 0. This one is about 8 times faster. Ignore it. This is about 8.5 times faster. Ignore it. So there's my first order approximation. Keep that pole. Keep that 0. Add a gain to match the DC gain. So here's the form of it. Pole and 0. Pick K to make the DC gain match up. So here's what it should be. Here's what it is when K is 1. K should really be 0.88. Here's g of s. That's my first order approximation. If I plot the two step responses, here's the first order approximation, here's the fifth order system. This actually does have a D matrix that models all the other states quickly decay, then I get the slow state. That's my first order model. Problem 3. What initial conditions decay quickly? What initial conditions decay slowly? That's actually an eigenvalue eigenvector problem. If I find the eigenvalues and eigenvectors of the A matrix, here's the eigenvectors, eigenvalues. I've got fast modes and a slow mode. Here's the slow mode. This initial condition decays slowly. That kind of makes sense. This is your V1, V2, V3. Primarily, if the initial condition is V3, it decays slowly. Going back to your circuit, that kind of makes sense. If the initial condition is V3, so this guy's charged up, pretty much everyone else is dead, this will decay slowly with a real pole. Again, not too surprising. If I try that, make this my initial condition, find the step response in MATLAB, and to do that, I use this form. I make my B matrix my initial condition and find the impulse response. The way that works is the integral of an impulse is 1 at t equals 0. That's my initial condition. Then it decays. Find the impulse response, and that decays as e to the minus 0.9t. In contrast, if I make the initial condition a different eigenvector, like the first one, the first eigenvector has a pole at minus 8, just a decimal point, minus 8 plus j30. That'll decay as a decaying exponential. For a complex eigenvalue, I've got complex eigenvectors. If I take the real part, that gives me cosine function. Complex part gives me a sine function. So if I do that, find the impulse response, there's my decaying exponential. Decaying is e to the minus 8t, about half a second. Cosine 30t, about 10 radians per second. No, 5 radians per second, or 5 hertz, 30 radians per second. The initial condition also kind of makes sense. It's primarily V1, a little bit of V2. So if my initial condition is primarily V1, this has the most voltage, a little bit on V2. The energy just bounces back and forth between the two with the inductor. And there's another eigenvector, eigenvalues as well. Problem 4 then. Let's look at a 10-stage RC filter. This also satisfies the heat equation. Find the dynamics for a 10-stage RC filter. Now this looks daunting, however, due to symmetry, if I find the dynamics at node 1, I pretty much find it everywhere except node 10, the oddball. At node 1, I've got the current. These three currents add together give me the current I1, which is C dV dt. Current from the left is V0 minus V1 over 3. Current from the right, V2 minus V1 over 3. Current up, 0 minus V1 over 150. Plugging them in, I get these numbers. Due to symmetry, I'll have the same equations everywhere up to node 9, so just change the index. Node 10 is the oddball. I don't have this term on node 10, so I get these equations. Basically what's happening is if I add voltage, I lose 67 units of current. 33 goes right, 33 goes left. The excess current goes to ground through the 150 ohm resistor. In state space, I can express that this way. Here's your x dot equals ax plus bu. Here's your A matrix. Most of the terms are on the diagonal. That's as I raise the voltage on any given node, I lose 67.33 units of current. 33 goes left, 33 goes right. Except the last node, that one's the oddball. If I put that in MATLAB as a 10 by 10 matrix, here's one way. It's a sparse matrix. Most terms are 0. With symmetry, just go down the diagonal. The diagonal is minus 67. Off diagonal is 33. Oddball, this guy is 34. I get the matrix into MATLAB and put the B matrix, C matrix, D matrix, state space, transfer function. This is where MATLAB really shines. One of the many ways where MATLAB shines. If I can get the dynamics in state space form, I can find the transfer function. This would be really painful by hand. Not too bad with MATLAB. What this tells me, this kind of tells me the step response. The step response looks like this. The settling time is 4, over 1.4 seconds. No overshoot. Here's your DC gain. That's what the step response looks like. When I come up with the second order approximation, I keep the dominant pole for sure. And let's use the number 10. Anything bigger than 14 I ignore. So keep this one. Ignore everything bigger than 14. That's my second order model. Plus fudge factor on top to match the DC gain. If I guess 1 from an initial guess, adjust it to make the DC gain match up. Here's my second order model. We'll plot the step response of the 10th order system versus the second order system. Same shape, same settling time, same DC gain, basically the same system. There's an extra delay in the 10th order system that I haven't taken into account. The more terms you add, the more accurate the model. If I could add a delay, that would work, except delays don't work really well in state space. So that's kind of one of the reasons we don't use delays. They just don't model well. But if you could add a delay, it matches really, really well if you had a 15 millisecond delay. That 15 milliseconds was added, or 150 milliseconds was found by trial and error. This slide it around until the two match up. Finally, problem 6 is what initial condition makes it decay slowly, what initial condition makes it decay quickly. That's an eigenvalue eigenvector problem. In MATLAB, I've got a 10 by 10 matrix, I've got 10 eigenvectors, I've got 10 eigenvalues. The fast eigenvector decays as the fast eigenvalue. If this is my initial condition, that decays as e to the minus 131t. If that's my initial condition, decays as e to the minus 1.4t. So to see that in MATLAB, here's my function. So I'm going to come up with the A matrix, find the eigenvalues, eigenvectors. If my initial condition is 0 and my forcing function is 1, here's the time response. So there's the step response of the system. If I want to get instead a natural response, I'm going to make the initial condition right here. Let's make it the fast eigenvector. And make the forcing function 0. And down here, let's just go from minus 0.2. If that's my function and I run it, poof. Did you see that? That's my fast eigenvector. That decays as e to the minus 131t. Let's slow that down a little bit. Let's go for 0.2 seconds, 10 times slower. If you notice, the shape stays the same. The amplitude is the eigenvalue. That decays as e to the minus 131t. The shape is the eigenvector. We go plus minus, plus minus, plus minus. That quickly goes to 0. Let's look at the slow eigenvector. If that's my initial condition, too much. That decays slowly. Let's run a little bit faster. And go for 2 seconds. So this is 10 times faster. The shape is the eigenvector. The amplitude is the eigenvalue. That shape is the slow eigenvector. And there are 10 eigenvectors. Here's another one. I kind of lose insight when you get to the other ones. But again, you notice the shape will stay the same. That's the eigenvector. The amplitude decays as the eigenvalue. Okay, so that's the fast mode, slow mode. What happens if the initial condition is random? Well, let's try it. Here's a random initial condition. Slow it down a little bit. I've got this shape. That's my slow eigenvector. That's not just random. What's happening is if I give it a random initial condition, I've excited all eigenvectors. the quick modes decay quickly, leaving the slow mode. So when you see a system decay, after a short period of time, all that's left is the slow eigenvector. So what you're looking at eventually is an eigenvector. That's the slow mode. So there, everything was excited. The quick modes are going away. No matter what initial condition I give it, pretty much, all that's left after a short period of time is the slow eigenvector. So we're kind of doing this because eigenvalues and eigenvectors, very few people understand what they are. This is where you kind of see what they are. Eigenvectors tell you the shape. Eigenvalues tell you the speed. And that's homework set number 2 for ECE 463-663 modern control.